So our next topic is difference quotients, and you may or may not have seen difference quotients before. So I definitely want to make sure that we're, paying attention to this and get to see a few examples about it. It's not really that complicated. It just requires a little bit of simplification. But a difference quotient is a tool that's used a lot in calculus to define what we call the derivative. And you might see it come up in pre-calculus as well. So it is a really important thing to know how to calculate, and that's why we see it coming up right now. But we're not going to go diving super deep into it, into the realm of calculus just yet. So at this point, we just want to know what this name is, a difference quotient, and that we have a definition for it. So our definition of a difference quotient of f of x is f of x plus h minus f of x all over h. And here h is just a positive real number. So h is just a number, just think of it just like x, but they're not the same number, right? X and h are representing two different numbers. And so here, all we want to do is find the difference quotient, so figure out what this is for a function f of x equals x squared. So for this first example, just kind of follow along with what I'm doing, and for the next two examples, try to do them as I'm, explaining how to do it. So here we want to do f of x plus h minus f of x all over h. Okay, so f of x, remember, a function is a rule. It says what you plug in, x, and it tells you what to do to it. So here we are squaring x, right? We're squaring whatever we put in. So if I put in x plus h, then I'm going to square x plus h. I'm going to square that whole thing, and then I'm going to subtract f of x. Well, f of x is defined as x squared. So I'm just going to write minus x squared all over h. We don't know what h is, it's just some other number, so we'll leave it like that. Well, the numerator I can simplify, right? I know how to square a binomial. So here I have x squared plus 2xh plus h squared, right? If we distribute everything out, and I'm subtracting x squared from that, and this is all over h. And here we notice that the x squared terms actually cancel, right? So I'm actually left with 2xh plus h squared all over h. And we'll see that this is actually a pattern of what happens when calculating the difference quotient, but here we actually now can factor an h out of the numerator because now we got rid of all the terms that didn't have h. So I can factor that out, and I'm left with 2x plus h all over h. Now I can cancel, I can divide by that h, and I'm left with 2x plus h. So this would be our final answer here. It would be our difference quotient. Now in calculus, we would study what happens as h gets really small, as h goes to 0, and that's called a limit, but we won't talk about that too much right now. Just know that this is the difference quotient, and it will come up later if you continue taking math classes. All right, so let's do another one. Here we have g of x equals 10. So here we just have a constant function. I just want to make sure we see what to do when we just have a constant. So we want to do g of x plus h minus g of x all over h. And now with a constant function like this, my input is x, or whatever my input is, and my output is always 10. So if I plug in x plus h, I'm still just going to get 10 from this function because it's always 10. So g of x plus h is 10 minus g of x, which is 10, all over h. Well, this is just 0 divided by h, so this is 0. And if we think about it, it didn't matter that we had a 10 here. It could be any number. So this gives us kind of a rule that always happens. Every constant function has a difference quotient, which I'm abbreviating as dq, equal to 0, right? Because this will always happen. And the difference quotient is actually measuring how a function is changing. So if we think about it, a constant function doesn't really change. It stays the same. It's always 10, or it's always whatever number it is. So it makes sense for the measurement of how it changes to be 0. All right, so that would be our difference quotient here. And now we're going to do one more example of this. And here we have something a little bit more complicated. We could try to do this with any function. So I'm not going to make things too bad, but here we have 5 minus 2x cubed. Now take a moment and try to do what we just did. This will be more similar to the first example, but try to do what we just did, pause the video, and try to find the difference quotient of this function. All right, so we're going to do f of x plus h minus f of x all over h. So here, plugging in x plus h in for x, we're going to have 5 minus 2 times x plus h all cubed minus, and I'm going to put parentheses because now I have more than one term. I don't want to have the wrong signs. So minus 5 minus 2x cubed all over h. So just like in our first example, we're going to have to multiply out x plus h all cubed. And remember, x plus h all cubed is not equal to x cubed plus h cubed, right? We actually have a binomial theorem. I don't know if you've ever seen that Pascal's triangle where you have one, a second row of ones, and then you add the previous two. You might have seen this a long time ago, or maybe not. But each row of this triangle we get by adding the previous two numbers. And this gives us the coefficients when we multiply out something like this. So when I have cubed, I'm going to follow this row. And so when I multiply that out, I'm going to have x cubed plus 3x squared h plus 3xh squared plus h cubed. So I'm decreasing the powers of x and I'm increasing the powers of h as I fill that in. And my coefficients are 1, 3, 3, 1, just like this row over here. Okay? And I have a negative 2 out front and I have this 5, so I'm going to just rewrite everything. All over h. And now if I distribute everything, I'm going to have 5 minus 2x cubed minus 6x squared h minus 6xh squared minus 2h cubed minus 5 plus 2x cubed all over h. Now if we look at what we can cancel these 5's, and we can also cancel the minus 2x cubed with the plus 2x cubed. And now we're actually left with things that only have h's in the numerator. So I'm also going to factor out that h like I did in the first example so that we can cancel it. So I'm going to have negative 6x squared minus 6xh minus 2h squared all over h. Make sure that makes sense to you, this step. And I'll cancel those h's. So really I'm just left with what's inside the parentheses as my difference quotient. Okay. So we should notice a pattern that this h will cancel out when we're calculating this, and that's not a coincidence. So make sure that we're going all the way to the end where we've canceled out that h. And we might still be left with some h's in the numerator, but that's okay. All right.